So what are now the options? If we assume that Sirius A and Sirius B have the same temperature, that means that the radius of Sirius B had to be 100 times smaller than Sirius A, because 100 to the power 2 is 10 to the 4th. And if the star is 10 to the 4th times fainter, that would be possible if Sirius B is simply 100 times smaller. So they would have the same temperature, but Sirius B would be 100 times smaller. That was a completely unacceptable possibility, because if it is 100 times smaller than Sirius A, 100 times smaller than the Sun, then the volume is 1,000,000 times smaller. But we knew already that Sirius B was about 1 times the mass of the Sun, and that would Sirius B have a density of 1,000,000 grams per cubic centimeter, 1,000,000 times more than our Sun, 1,000,000 times more than the density of water. And that was completely unacceptable by the community. So it was dismissed that Sirius B was 100 times smaller. Well, then you have only one other choice, and that is you can make the temperature of Sirius B 10 times lower than Sirius A, because 10 to the power 4 is also 10,000. So you have a choice. Either you make the radius 100 times smaller, or you make the temperature 10 times smaller. And of course, the radius 100 times smaller was rejected, and so it was assumed that Sirius B was just a very cool star, and that therefore Sirius B was so faint. In 1915, the temperature of Sirius B was measured. That was at the time that astronomers were starting to work with spectroscopy. They took spectra of stars, and when you take a spectrum of the Sun, you see all the colors from red all the way to blue. And if you give these spectra to an astronomer, they can tell the temperature of the star by looking how much blue there is and how much red there is. If there's a lot of blue, the star is very hot. If there's a lot of red, the star is cold. And Walter Adams concluded that Sirius B had a temperature of 8,000 degrees, and so Sirius B was not at all cold. The only conclusion, therefore, was that Sirius B had to be 100 times smaller. And so there was no escape anymore. There was here a star in the sky which had about the mass of the Sun, and it had a volume which is 1,000,000 times less than our own Sun, and therefore it had an absurd density of about 1,000,000 grams per cubic centimeter. And that was the discovery of a white dwarf. If you take 1 gallon of water, that weighs 8 pounds, if you take 1 gallon of white dwarf material, that weighs 24 million pounds. I'd like to show you a picture of Sirius A and Sirius B. It's the next picture. You can make it a little darker. I don't think I have to explain to you which one is Sirius A and which one is Sirius B. So B is 10,000 times fainter than A. And this is more or less what Alvin Clark must have seen when he tested his father's telescope. Yeah, we can have the lights back up again now. So now I will turn to neutron stars. In 1930, Chandrasekhar calculated that the maximum mass of a white dwarf could only be about 1.4 times the mass of the Sun. It's not a trivial calculation. It's a quantum mechanical calculation. If the mass were larger, he concluded that the white dwarf would collapse onto itself. Not knowing what would happen, all he concluded was that the star would collapse onto itself. Neutrons were discovered in 1932 by Chadwick, for which he was awarded the Nobel Prize. And then there were 2 astronomers in the world in 1934, Zwicky and Bade, who speculated that somehow neutron stars may exist. A star that is practically only made of neutrons. And they even made the daring prediction that these neutron stars would be formed in what we call a supernova explosion, and I will explain to you shortly what a supernova explosion is. I'm now going to turn to stars which are more massive than 8 times the Sun, but less massive than 25 times the Sun. So we have already dealt with white dwarfs. Those are the ones that come from stars lower than 8 solar masses. We're now going to neutron stars. Between 8 solar mass and 25 solar mass is the original star. Well, hydrogen starts to burn to helium. Hydrogen comes to an end. Star shrinks. Temperature goes up, helium ignites. Helium is being used up. Star shrinks, the core shrinks. Temperature goes up, carbon starts to burn. Carbon is making oxygen. Carbon burns up, star shrinks, temperature goes up, oxygen takes over and forms neon. And this process continues. Every time there is a new element that takes over the thermonuclear burning, every time what happens is that the core shrinks, goes up in temperature, and a new thermal reaction can start. And the last one is silicon, which burns to iron. And there is an enormous difference in temperature in the core between the hydrogen burning phase early on and the silicon burning phase at the end. The hydrogen burning phase, a typical temperature of the core, is about 30 million degrees. Our sun inside is about 15 million degrees. But when silicon burns to iron, the core has a temperature of about 3 billion degrees. So now we end up with an iron core, and that's when the thermonuclear reactions stop, because iron is a very stable element. And now comes the issue that the iron core cannot be any larger than 1.4 times the mass of the Sun, because Chandrasekhar had told us that that object could not support itself. But if more mass does fall onto the iron core, it will collapse. And indeed, the white dwarf that you have formed then will collapse. Electrons will be pushed into the protons, and they will make neutrons, and they end up then with a neutron star. And so the neutron star is the result of the fact that you have exceeded the Chandrasekhar limit. This process, whereby the white dwarf collapses into a neutron star, creates an enormous amount of energy, because it turns out that the size of a neutron star is only about 10 kilometers, and the size of the white dwarf was 10,000 kilometers. And so the star becomes 1,000 times smaller, the core, and if it becomes 1,000 times smaller in size, then the volume becomes 1 billion times smaller. That means the density of a neutron star is 1 billion times higher than the density of a white dwarf, and the density of a white dwarf was already absurdly high, namely 1 million grams per cubic centimeter. But the neutron star is 1 billion times more dense, becomes 10 to the 15 grams per cubic centimeter, which is higher even than what we consider normal nuclear density in nuclei. And the energy that is produced in this falling in, gravitational potential energy being converted to kinetic energy, is so huge that the energy that is released in a fraction of a second is more than the energy that our sun radiates in its entire lifetime. In fact, it can be 100 times more. So that one conversion from a white dwarf to a neutron star, which happens in a fraction of a second, produces 100 times more energy in that 1 second than our sun can do in its entire lifetime of the sun. That is an enormous amount of energy, and the whole thing blows apart and that is what we call a supernova explosion. How were these neutron stars discovered? They were discovered by a graduate student who has the name Jocelyn Bell. She worked in England, in Cambridge, England. Her supervisor, Anthony Hewish, had designed a new type of radio telescope, and Jocelyn was hired to record the data every day on her bicycle, would look at the strip recorders and look at the data, whether there was anything new.